sure that it's true, right? That the sum, we want to show that the sum of n terms of the arithmetic sequence with a first term of 1 and a common difference of 2, with the formula for the nth term is 2n minus 1, that the sum equals n squared. So the first step is show that it works for n equals 1. Okay, meaning plug in 1 to the formula here. So if you put in 1 for n, you're going to get 1 squared, which is 1. Okay, the sum of the first term you can plainly see in front of you is 1. So that checks. 1 squared equals 1. That is the same. So the first step is done. Okay, now we want to show, we want to assume it works for n equals k, and then show it means it works for n equals k plus 1. Well, if the sum of the first k plus 1 terms is this, right? It's the sum of the first k terms, right? It's like this thing right here, just put a k in the place of n, plus the next term, that's the k plus 1 term, right? And then this is the sk plus 1. So in this step, what we're going to do now, we're going to assume that this formula works for the first k terms by substituting for all of these terms with k squared, right? That's what sk is. If you just put a k in the place, sk is k squared. So k squared plus ak plus 1 equals sk plus 1. All right, that's what all of this is here. The k squared is here. Right, the ak plus 1 is what you get when you put a k plus 1 in the place of n. So that's what this is. And the sk plus 1 is k plus 1 squared. That's what you get if you put k plus 1 in the place of n there. Now, we don't know that that's true. Yeah. Here? Yeah. Because this is the formula for the nth term. So the formula for when n equals k is 2k minus 1. So remember that the second step of math induction is show that if you assume the formula works for n equals k, that it must work for k plus 1. By plugging in place of all these terms, k squared, we just assumed that it worked for n equals k. That's the assumption part. Right? Now we need to show that, in fact, this case, the sk plus the next term, which is ak plus 1, equals the sum of the first k plus 1 terms using the formula. So we don't know that that's true. That's the part we've got to show now. We assumed that it works for n equals k by substituting k squared. We need to show now that the left-hand side equals the right-hand side. That's why I put a question mark on the top. I don't really know that that's true until I've gone through the process here. Well, let's see. On the left side, I can use distributive property here, right? That'll give me 2k plus 2. So now I've got k squared plus 2k plus 2 minus 1. On the right side, k plus 1 squared is k plus 1 times k plus 1. Here I can combine some like terms. That is k squared plus 2k, and then 2 minus 1 is 1. And on the right side, k plus 1 times k plus 1 is k squared plus 2k plus 1. Okay, now the left equals the right. So I just showed that by assuming it works for n equals k, it works for k plus 1. That's the second step of math induction. And now, since we know it works for n equals 1, it must work for n equals 2. And if it works for 2, it works for 3, it works for 3, it works for 4, to infinity. So it works for all values of n. So we could use this formula. We could with any value of n, and we know that it works.